So when you see this chapter, linear momentum, and then it's tied with collisions, you know that linear momentum is related to collisions. Of course, that's why you have both in the same chapter. Essentially, linear momentum is used to study collisions. And also, when you hear about linear momentum, you know there's some other momentum coming. Otherwise, why would you call it linear momentum? Yes, there is also angular momentum. What is the difference between the two? In linear momentum, you're looking at the momentum of objects that move in straight lines. In angular momentum, you're looking at objects that rotate. So in fact, for every linear quantity, you'll also have a rotational quantity. The last chapter of this section of what we've been doing is called rotational motion. The last chapter, which is incredibly tough because everything that we've done in all the other chapters will come into play in that chapter. That will be the climax, kind of. So anyway, so that's linear momentum. And haven't we defined linear momentum before here? I think we have. It's simply the product of mass and velocity. Linear momentum is the product of mass and velocity. That is what it is. Mass and velocity. It's represented by the letter P, as you can see on the screen. And P is supposed to be a vector, so I'm going to try to add the vector symbol there. And since it's a vector, it should have a direction. And the direction of linear momentum is simply the direction of the velocity. So if an object is going to the north, the momentum is going to be to the north. If the object is moving to the south, well, of course, the momentum is going to be to the south, right? So momentum is the product of mass and velocity. What is the unit of momentum? Just put their units together. You will get the unit of momentum, which is kilogram meter per second. It doesn't have any particular new name for that, so you'll have to write the whole thing. The unit of momentum is kilogram times meter per second. That is the unit. Okay. That's pretty simple. Now we'll try to relate force to momentum. What is the formula for force that you know? Net force is equal to mass times? Acceleration, right? But acceleration is the rate of change of velocity, isn't it? So A can be written as dv by dt. So that makes it m dv by dt. Because acceleration is dv by dt. Now you know that in differentiation you take the constant out always. So what I'm going to, in almost every case that we study, mass is assumed to be a constant. Mass never changes. Therefore, can I write it this way? Will it be the same? It will definitely be the same because then you know mass can be taken out because it's a constant, right? So, well, that's interesting. What is this quantity called? Momentum. So we get a new definition for force. Net force is equal to change in momentum by time. So net force is dp by dt. That is another way of expressing force. dp by dt. Shouldn't force be a vector or is it a scalar? Force, please? Vector. Now, I just want you to think as well. It's not about writing down and not thinking. You know that. What if this is non-existent? What if there is no external? Oh, well, of course, you know this stands for external force, don't you?
Yes.
It's not internal force, it's external force. So, what if there are no external forces acting on a system? What happens to the left-hand side? Zero. But that stands for dp by dt, which means no momentum? No. Which means dp by dt is equal to 0. What does that mean? That means momentum is a constant. Are you getting what I'm saying? Net force is 0. dp by dt is 0. You're not saying momentum is 0. You're saying change in momentum with respect to time is 0, which means there is no change in momentum. So we come to a very important principle. It's called the principle of conservation of momentum, which comes with a condition. What's the condition that we talked about? The net external force has to be, you're still not paying attention. That it's not, yeah. The net external force has to be, that's, thank you. Thank you. Concentration is key. If the net external force is 0, then the system will have a constant momentum. That's called the principle of conservation of momentum. So for example, since you're looking at me and saying, what is he talking about? Okay. For example, if two objects collide with each other, say two objects collide with each other. When they collide, will they be exerting forces on each other? Yes. But taking this as a system, wouldn't that be an internal force? Like you have two objects colliding. That is a system. Two objects together form a system, right? So you're not kicking them when they collide. Well, that would make it an external force. But if it's only one exerting a force on the other, of course, the reaction, that's an internal force. See? So when two objects collide, we're going to say that the total momentum before collision will be exactly equal to the total momentum after collision. That is a very important principle that we're going to use here. Although it's not written there, we're going to use that. If the net external force is 0, dp by dt is equal to 0, and p is a constant. I'll stop right. If you decrease the volume, what happens to the pressure? Now that you can understand. When you decrease the volume, the gas molecules are mad now. They have less space to move, right? So wouldn't they be making more collisions with the walls of the container in a second?
Yes.
In another chapter, we are actually going to derive the formula for pressure based on the collisions that the molecules make. For the first time in your life, you will actually see why the pressure depends on volume, why it depends on temperature, without just saying Boyle's law, Charles' law. You'll actually go into the concepts and you will see it. It's coming. So gas molecules do create pressure because of the collisions. Now we are moving on to the second concept, which is impulse. Impulse. Look at the diagram and you will understand something. There are two quantities given there, force and time. What does that mean? That means the change in momentum of this soccer ball depends not only on the force applied, but also on the time for which you apply the force. Right?
Yes.
Which means, look at the second diagram. If you apply the same force, but for a longer time, as you can see, twice the time, what happens to the change in momentum? It's double. So it's not just how long you study, it's also how much concentration you have when you study. Both, yeah, that's my force and time. Some people think it's only the time. No, it's how much concentration. So both together, if you take both together, multiply them, you will get impulse. So what's impulse? Impulse is the product of the force and the time for which it acts. Simple. Impulse is the product of the force and the time for which it acts. The symbol for impulse is given by J. It's a vector. Again, impulse is a vector. So impulse J is integral ft dt. Whenever you have small quantities, you bring in the integration. Wait, I want to stop here and just, why? See, I started saying impulse is force multiplied by time, correct?
Yes.
Which is true in a college physics class, which is correct. But then why should I go to integral ft dt? Somebody tell me why. Why can't I just keep saying it's the product of force and time? If I get that answer, I'll be really excited. Think about the force applied by a tennis racket on a tennis ball. I'm talking about long tennis. They hit it hard, right?
Yeah.
Think about it. In slow motion. Just before the racket hits the ball, what's the force applied on the ball? Just before it touches, what's the force applied?
0.
Thank you. Zeros are exciting. Say it. Okay, 0. And then in slow motion, what's going to happen to the force applied as it makes contact? What's happening to the force applied? Is it a constant force?
No.
Or, because you just now said it's 0, that means it's going to go from 0, the force is going to increase. Then as it releases, I hope you can visualize, right? As it lets go, what's going to happen to the force now? It's going to go down, decrease. So is it a constant force or is it a varying force? That's why we have to use integration. So it's not a simple product. It is not a constant force. It's acting for a certain time, but during that time, the force goes from, I hope you understood, the force goes from a 0 to a maximum back to a 0. So when you have a change in quantity, that's when you use integration. I hope you know that. So that's why it's ft dt. Now simple math. But what's f? Isn't it dp by dt?
Yes.
Come on. Yeah, so it's dp by dt. You see the limits of integration, t1 to t2. And the simple math there will show you that since you have dt here, it's just integral dp. What's integral dp? P. And then when you substitute the limits, what do you get? P at t2 minus p at, which is simply change in momentum, isn't it?
Yeah.
Oh, so impulse is also change in momentum. So there are two formulas for impulse. One is integral t1 to t2 ft dt. Just added the limits there. Integral t1 to t2 ft dt, that's one formula for impulse. Second one is impulse is change in momentum. You look at the x-axis, you find its time. And then you look at the y-axis and you find its force. Of course, this graph is drawn for the impact force created by a meteor, isn't it? And so, look at the forces here. They are huge forces, but I want you to understand that the force goes all the way from 0 to a maximum. Do you see this? Well, it's not like a tennis racket. Here, at 0 time, the force is maximum, and then the force decreases continuously. Are you with me? Come on. So if you integrate f dt, what will you get? You will get the area of this graph. I hope you're paying attention. What would you call that? It's called the impulse.
Yeah.
Just now I told you impulse is integral ft dt, right?
Yeah.
So that's the third way of finding impulse. How? The area of the force time graph gives you the impulse. So actually it's this area that gives you the impulse. But look what's done. If you take the average of this quantity, the biggest force, and the smallest is a 0, wouldn't you end up somewhere here?
Yeah.
That is the average force, see? And then if you assume that it was the average force that was acting for that entire period of time, and then find the area of that part, if you are looking carefully at this graph, you know that the two areas are going to be the same. I hope you understood. Did you look at that? Look at the area of this rectangle. Isn't that going to be the same as the other area under this curve? Yes. It is. Now, isn't this the average force? Come on. Yeah. So that means there is a fourth method of calculating impulse. What is that? Average force multiplied by the time. So there are 4 ways of calculating impulse. Number 1, the actual definition, integral ft dt. Number 2, which automatically gives you the area of the force time graph, right? Number 3, impulse is change in momentum. Number 4, you multiply the average force with the time taken, you get the impulse. 4 methods of calculating impulse. I hope you got it. That is definitely a collision. And that's why when a collision happens, you need to have seat belts on. We've spoken about that many times. And then, well, sometimes in a collision, the airbag pops up, as you can see. And then how does the airbag actually save us? Give me the detailed description of what the airbag does. Well, let's say that if the airbag was not there, you're going to hit the steering wheel, right? Yes. All right. Now you're going to have the airbag pop up. So 2 different cases. What's the difference between these 2 cases?
It decreases the force with what you hit.
How does it decrease the force? Or why does it decrease the force? Very good. So the impulse in both these cases are the same. If there was no airbag, you're going to have a huge force for a small time. You see that? Yes. Big force and you stop immediately. You stop. That's a huge force. If there's an airbag, it cushions it, which means that force acts for a bigger amount of time. Therefore, the force is reduced. But the impulse in both of these cases are the same. We've been talking about this. If somebody throws a fastball at you, when you catch it, you pull your hands back. If you have to jump from a burning building, you jump and bend your knees. We've spoken about that. Yes. Or if you have a chance, jump onto sand instead of jumping into concrete. In all these cases, what are you doing? You're increasing the time. So remember, impulse is constant. But if you increase the time, you reduce the force. Is that clear? Yes. That's what we're talking about. That is the practical application of everything that we've been talking. What is that? Okay, so right now, you see a collision taking place on the screen. There are 2 objects. What are their masses? M1 and M2. What velocities are they moving at before collision? V1 and V2. And then they collide. When they collide, they will exert a force on each other, right? So you can see that F12 is the force exerted on 1 due to 2, which is exactly the opposite of the force on 2 due to 1. That's Newton's third law, right there. Hello? That's an internal force. I've told you that already. And if the external force is 0, we know the momentum is conserved. That means the total momentum before collision. What is the total momentum before collision? It's the momentum of this plus the momentum of that. What is momentum? The product of mass and velocity. So does this make sense now? Yeah. M1v1 plus M2v2, which is the total momentum before collision, is equal to the total momentum after collision. That is called principle of conservation of momentum. So I thought I should apply this in the case of a recoil of a rifle. Everybody knows that if you fire a rifle, you have to have the back part or the butt of the rifle against your shoulder. It's called recoil. Everybody knows that, right? Yes. Come on. You can say it's like action and reaction, but it's more than that. It's the conservation of momentum. Conservation of momentum is actually based on Newton's second law and third law. See that? That's the difference. It's second and the third law. So let's get a formula for recoil of a rifle. Easy, easy. Before you fire the rifle, what's the bullet doing inside the rifle? Dancing around? No. Yeah.
Resting.
What's its momentum? Okay, before you fire, I don't think anybody shakes the rifle. So the momentum of the rifle is also 0 before firing, right? Absolutely still. Therefore, the total momentum before firing is 0. So, here it is. I just gave the velocities. Velocity of the bullet, B stands for bullet, mass of the bullet. Total momentum before firing is 0. I think everybody got that. Just now I told you. And after firing, this is the momentum of the bullet. This is the momentum of the rifle. Right? Simple math shows you that when you rearrange, you're going to get the velocity of the rifle as negative. Product of the mass of the bullet, velocity of the bullet divided by mass of the rifle. What does the negative sign show you? That the rifle is moving backwards, right? And how do you know that this is going to be a small number? What do you have in the denominator? Yeah? Mass of the rifle. Isn't that considerable? Look at this ratio. The mass of the bullet by the mass of the rifle. Isn't that going to be a really small?
Yes.
That's why, although the velocity of the bullet is big, the recoil velocity of the rifle is going to be small. Everybody got that? Good. We will see. Once you take the quiz, we will see how many got what. You'll have a Socratic quiz at the end of this lecture. I didn't tell you at the beginning. On purpose. Look at this and tell me something. What's it talking about? Hockey pucks. Is this a case of negligible friction or a case of considerable friction? Negligible friction. So that means there is no external force acting, you see? Because if there is friction, that would be an external force. Study the diagram and tell me what you understand. If there is no friction, you should surely be able to tell me the velocity of this puck. If you cannot, you're wasting your life in here. Sorry for laying it out that way. Because isn't that a collision?
Yes.
It is a collision. And don't you know that in a collision, the total momentum before should be equal to the total momentum after?
Yeah.
And these two have the same mass, of course. Hockey pucks. No external force. So don't say it. How many people know the velocity of this one after collision? Put your hand out. I'm compelling people to put it out. Shout it out. Zero. Isn't that what you see? Haven't you seen it? It'll go and hit it and it'll go and sit there. The other one will fly away at that. How many of you know the game called caroms? Carom board? I don't know. You've never? Okay. Same thing. Marbles, yeah, same thing. But this is a more like frictionless case. That's why it's interesting. Talking about collisions, there are two types of collisions. Two types of collisions. One is called an elastic collision. The other is called an inelastic collision. Elastic and inelastic. Let me check if you have been listening. In which of these two cases will momentum be conserved? In which of these two cases will momentum be conserved? Did I talk about these two before I taught you the conservation of momentum? No. So I'm talking about this after, right? What does that mean? And all this time I've been saying, in any collision. Haven't I been saying that? In any collision. Come on. Haven't I been saying that? I've been saying, in any collision, momentum is? So what's your answer? Which of these two cases is momentum conserved? You got to have courage in both. So what's the difference? In an elastic collision, kinetic energy is also conserved. In an inelastic collision, kinetic energy is lost. Means not conserved. So in both of the collisions, momentum is conserved, but in an elastic collision, kinetic energy is also conserved. In addition to momentum, here kinetic energy is not conserved. And I started speaking about it with this picture. Take a look at it. You can make out what it is, right?
Yeah.
Yeah? Have you heard of a deuteron? That's how you get a deuteron, a proton colliding with a neutron. And you see what happened after collision? What happened? What happened after collision? They stick together. If two objects stick together after collision, that is a perfectly inelastic collision. Remember that. If two objects stick together after collision, it is a perfectly inelastic collision. That means maximum kinetic energy is lost. Right? Maximum kinetic energy is lost. So the world outside will say stick together. That's a different meaning. It's always good to stick together, but in collision, no. If you stick together after collision, you lost maximum kinetic energy. We're going to work out a problem soon where a sports car runs into an SUV parked at a red light and their bumpers lock together and then they move off. It's a very interesting question. And the police are able to calculate the speed of the sports car. We're going to do that. Just by looking at the tire marks on the road, the police are able to measure the tire marks. All right, this is how much you push that SUV, and then they will make calculations using kinetic friction. It's true. And then say, oh, this is the speed at which you were driving. And therefore, this was above the speed limit, especially when you have a red light there. The SUV had been stopped there at the red light. This guy comes and hits him. Are you listening? Yeah. So we're going to do that problem. But that's again a case where after collision, two objects stuck together, right? Do you hear any noise when that happens?
Yeah.
Sports car running into an SUV?
Yeah.
So you have sound energy. Sometimes sparks are produced. Sometimes it can catch fire. Come on.
Yeah.
You all, right? So where did all that energy come in? Sound, heat, light, where did all that come in from? Where did you get all that? The kinetic energy of those objects. They're making sense now.
Yes.
So that's why I'm saying kinetic energy is not conserved. Maximum kinetic energy is lost. Because the kinetic energy which it had has been converted into sound, light, and I don't know what, heat, everything. Are you getting what I'm saying? Okay. So that's a case of perfect inelastic collision. I think we should soon move on to problems, but I just wanted you to get this particular case of an elastic collision. Will momentum be conserved?
Yes.
In both the collisions?
Yes.
Okay. We are only looking at elastic collisions soon, but first I'm writing the difference there for the 5th time. Makes sense, right? So, before collision, and we were talking about an elastic collision now. What's that? Where did I get that from? What is that? Isn't that just conservation of momentum? Yeah. And isn't kinetic energy also conserved? Yeah. So what's the formula for kinetic energy? Okay. 1.5 times mass times velocity squared. So I'm going to take the total kinetic energy before collision, set it equal to total kinetic energy after collision. And then a lot of math. No, a little math. So that is conservation of momentum. This is the conservation of kinetic energy. Total kinetic energy before is equal to total kinetic energy after. Now what I'm going to do is, in the next step, I'm going to take this term to the left-hand side and this term to the right side. So if I take this to the left-hand side, I already have one here, and the common factor would be the mass, isn't it? Right? I'm going to do the same with the second equation too. Watch. So in the first one, I have already taken that term to the left-hand side, taken the common factor out, and same thing on the right side. That's my equation 1. And then I'll do the same kind of thing, but can I just cancel these halves out? It'll be okay? Will it be okay?
Yeah.
Okay, I'll do that first. And then I will do the same exact thing. So collect the terms with MA on the left side and the terms with MB on the right side. And then I'll ask you, does anybody know what A squared minus B squared stands for? How can it be broken up like A squared minus B squared?
A plus B, A minus B.
Correct, A plus B times A minus B. All right, so I'm going to do that. So that is split into A plus B times A minus B, same thing on the right side. That'll give me my equation 2. Now can you divide equation 1 by 2 and tell me what you get? If you divide the left side with the left side of this equation, what's going to cancel out? That and that. What's going to cancel out? The masses, right?
Yeah.
And what about this term? Wouldn't that also cancel out? And I'll be left with only this term. And on the right side again, if I divide this with this, the masses are going to cancel out. Once again, this will cancel out, and I'll be left with this. So that's a very simplified equation that I'm getting. And then rearrange that, and I get my final result, which is really interesting. Now, students like this equation because any simple equation, they will fall for it. Now, do not forget, can you apply this equation for all collisions?
No.
You can only apply it for elastic collision. Please notice that. If any problem says it's an elastic collision or a perfectly elastic collision, you have the right to use this. Now, one more thing. You may not have noticed. Look at the left side and look at the right side. What difference do you find?
No mass.
Huh?
No masses.
No masses, but yeah, the masses got cancelled. But look at the order. It's the opposite, see? And do you know what this term is called in physics? It's called the relative velocity. The velocity of one minus the velocity of the other is called the relative velocity of A with respect to B, isn't it? So in an elastic collision, the relative velocities before and after are equal but opposite. I said it.